You need to build something, not in the abstract, theoretical sense of a construction project with planning permission and delivery schedules. In the immediate, practical, survival-dependent sense that ancient human life regularly produced. It is late autumn. The temperature has dropped enough over the past 2 weeks to make the situation clear. The current sleeping arrangement, which was adequate through summer, is not going to be adequate through what is coming. You need walls, you need a roof, you need an enclosed space that can be heated by a fire and that will hold that heat against the outside air temperature, which is heading somewhere that your body has very definite opinions about. You look around at what you have. No lumber yard, no hardware store, no concrete, no steel, no glass, no insulation and rolls, no fasteners and bags, no power tools, no blueprints, no building codes, no contractor with a 5-week timeline, and an invoice that makes your eyes water. What you have is the landscape around you, the raw, unprocessed, unmodified natural environment in its entirety, and the knowledge accumulated across your lifetime and the generations before yours of what that landscape can provide and how to make it work. This is the ancient builder's situation. And what ancient humans built from that situation, what they figured out how to do with stone, wood, bone, hide, plant fiber, clay, and every other material the natural world offered, represents some of the most impressive engineering in human history. Not impressive because it was primitive. Impressive because it was effective, adaptive, and in some cases technically sophisticated in ways that took modern materials scientists a long time to understand. Today we are going through exactly what ancient humans used to build things, how they used it, and why the story of ancient construction materials is far more interesting than most people have ever stopped to consider. Let's start with the most universal ancient building material: wood. Wood is the obvious first answer, and in forested environments, it was almost certainly the dominant construction material for most ancient human groups. But treating wood as a single category misses everything interesting about how ancient humans actually worked with it, because wood is not a uniform material. The properties of different wood species, their density, flexibility, resistance to splitting, workability with stone tools, resistance to rot and insect damage, strength to weight ratio, vary enormously, and ancient builders knew this in the kind of practical, granular detail that modern timber engineers know it in. Hardwoods versus softwoods is the broadest distinction, but the ancient builders' taxonomy went far beyond this. Ancient builders knew which species were best for structural elements requiring strength, the horizontal beams and vertical posts that carried loads, and which were best for flexible elements like woven walls and roof coverings. They knew which species resisted rot in contact with the ground and which would decay quickly, which was critical information for any structural element whose base was embedded in or near the soil. They knew which species split cleanly along the grain and could be reduced to planks and boards using stone tools, and which split unpredictably and were better worked in other ways. The evidence for ancient wood selection knowledge comes partly from the archaeological record itself. Where wood has been preserved, the specific species identified are consistently appropriate to the structural role they were used in, suggesting deliberate selection rather than opportunistic use of whatever was nearest, and partly from the ethnographic record of traditional construction practices, where detailed knowledge of wood species properties is consistently documented as critical specialist knowledge maintained and transmitted within communities. Structural wood preparation also went beyond simply cutting and shaping. Ancient builders used fire to harden wood for specific applications. The fire hardening of spear tips is well documented, but the same principle applied to structural elements that needed enhanced hardness or resistance to damage. Charring the base of posts that would be embedded in soil dramatically extends their functional life by creating a charred outer layer that resists the soil contact moisture and insect damage that kills untreated wood. Traditional builders worldwide have independently discovered this technique, and ancient builders in forest environments with fire available had both the knowledge principle and the practical means to apply it. Let's talk about stone, because stone construction in the ancient period goes significantly further than most people imagine. Stone is the ancient building material that the archaeological record documents most clearly, simply because stone survives what organic materials do not. The oldest confirmed human-modified stone structures are not glamorous. They are arrangements of rocks used as windbreaks, anchor weights for shelter coverings, and foundation elements for organic superstructures. But they are old, very old. At sites including Terra Amata in France, dating to approximately 400,000 years ago, Researchers have found arrangements of stones in patterns consistent with foundation elements for oval-shaped shelters, with associated post holes indicating that organic superstructures, wood, hide, plant material, were anchored by these stone foundations. Whether these structures were built by Homo heidelbergensis or represent a later occupation is debated. But the basic pattern of stone used as structural anchor for organic shelters appears early in the ancient record and continues through the full span of ancient human occupation. The use of stone for shelter walls, stacking rocks to create a semi-permanent wind and cold barrier, is documented at ancient sites across northern Europe and Asia, where the combination of cold temperatures and limited timber availability made stone attractive as a primary structural material rather than simply an anchor or foundation element. In these environments, ancient builders developed specific techniques for dry stone construction, building stable walls from irregular rock pieces without mortar that required sophisticated spatial reasoning about how irregular shapes could be nested and locked together to create stable structures. Dry stone construction looks simple from the outside. It is not. Selecting stones for their fitting properties, orienting them to interlock with adjacent stones, managing the distribution of weight through the wall to prevent collapse, and particularly managing the problem of wall corners, where two wall sections meet and must be mutually stabilizing, requires practical engineering knowledge that is not immediately obvious, and that produces very different results depending on whether it is applied or not. The dry stone walls that have survived from ancient and traditional construction contexts, some standing for thousands of years, are evidence of that knowledge applied correctly. Let's talk about bone and ivory, because in environments where timber was scarce and stone was available only in specific forms, bone and ivory became primary structural materials, and the structures built from them are among the most extraordinary in the ancient architectural record. We have discussed the mammoth bone houses of the Ukrainian and Russian steppe in other contexts, but their construction deserves re-examination through the lens of materials knowledge. The builders of the mammoth bone houses at sites like Mezhyrich and Mezin were working with a material that is simultaneously heavy, structurally strong, and extremely difficult to modify without the right knowledge and tools. They were selecting specific bones for specific structural roles, lower jaws for foundation elements, long bones for walls, shoulder blades and pelvises for specific structural positions, and tusks as arched roof supports, in ways that demonstrate a working knowledge of structural mechanics applied to an unconventional material. Bone and ivory have mechanical properties that differ significantly from wood and stone. They are somewhat elastic. They flex under load rather than cracking cleanly, which gives them specific advantages in applications where rigid materials would fail under the dynamic loads that wind and ground movement impose on structures. Ancient builders who worked extensively with bone and ivory would have discovered these properties empirically through experience with how these materials behaved under stress, and would have exploited them in their structural designs. The large mammoth tusks used as roof arch elements at some mammoth bone structures required preparation before use. The natural curve of the tusk had to be assessed and either worked with or modified to produce the specific shape needed for the structural role. Ivory can be modified through soaking in water and controlled application of heat, which changes its flexibility and allows it to be bent to new shapes that it retains on cooling. The knowledge that ivory could be shaped this way, and the specific techniques for doing so, represent a sophisticated understanding of material properties that goes well beyond simply using bones as found. Let's talk about plant fibers and woven materials, because this is the building material category that the archaeological record documents least well and that most people consequently think least about, despite the fact that woven plant fiber construction was almost certainly one of the most widespread and important ancient building technologies. Woven plant fiber, whether in the form of mats, baskets, rope, or more complex woven panels, has essentially zero preservation probability in most archaeological contexts. It rots completely, quickly, leaving nothing behind in most soil conditions. The archaeological invisibility of woven plant fiber construction is a preservation artifact, not an accurate reflection of how common or important it was. What we know from the limited cases where plant fiber materials have been preserved, in the extremely arid conditions of some Egyptian and South American sites, in the waterlogged conditions of some European peat bog sites, in the frozen conditions of some Siberian permafrost sites, is that ancient plant fiber working was far more sophisticated than the absence of evidence would suggest. Ancient basketry and woven mat construction visible in these exceptional preservation contexts shows techniques including twining, plaiting, coiling, and various more complex weave structures executed with precision and evident long practice. Woven plant fiber panels served specific construction functions that no other material served as well. As wall infill between structural posts, woven panels provided wind and rain protection with minimum weight, and with the ability to be quickly constructed, modified, and replaced. As roofing material layered in overlapping courses, a technique documented in traditional construction worldwide. Woven grass or reed panels provide effective weather protection through a simple structural principle. Each layer sheds water onto the layer below, and the cumulative shedding effect of multiple layers provides weather resistance far exceeding what any single layer could provide. The knowledge of which plant species produced the best fibers for weaving, which were strong, which were flexible without breaking, which resisted moisture damage, which could be split finely enough for tight weaving, was ancient specialist knowledge of exactly the kind that ancient communities maintained and transmitted across generations. The gathering, preparation, and working of plant fibers for construction was almost certainly a distinct technical domain with its own body of knowledge, its own specialists, and its own transmission pathway. Let's talk about hide and leather, because the same materials used for clothing were also critical construction materials in many ancient contexts. Animal hide, properly processed, is an extraordinarily versatile construction material. It is strong in tension, a property that makes it excellent for binding and joining elements, for covering frames where the hide is stretched over a structural skeleton, and for making rope and cordage. It is flexible. It can conform to complex three-dimensional shapes that rigid materials cannot cover cleanly. It is thermally insulating. A skin covering over a structural frame creates a layer of still air between the hide and the exterior that provides significant thermal resistance. And it is relatively water-resistant when properly processed, particularly when fat is worked into it to fill the pores of the skin. The use of hide as primary wall and roof material for ancient structures is documented in multiple archaeological and ethnographic contexts. The classic form is the hide-covered frame structure, a skeleton of wooden or bone poles, anchored in the ground or weighted with stones, bent and lashed together to create a structural form, then covered with prepared hides that are stretched over the frame and secured in place. This construction form is light, portable, rapidly constructed, rapidly dismantled, and thermally effective, exactly the properties required by mobile groups who needed adequate shelter without the weight and logistical burden of permanent construction materials. The processing knowledge required to produce construction-grade hide is substantial. Raw animal skin, if not processed, dries stiff and brittle, rots rapidly in damp conditions, and provides inadequate protection against the elements. Properly processed hide, the fat removed from the inner surface. The skin worked to break down and soften the protein matrix, treated to prevent rot, is flexible, durable, and weather-resistant. The specific techniques for producing this quality of processed hide from raw skins, brain tanning, smoke curing, fat working, the specific sequences of scraping and stretching required, are documented as sophisticated technical knowledge in traditional cultures worldwide. Let's talk about clay, because clay construction is significantly older than the fired ceramics that people typically associate with it, and has a construction history that extends back into the ancient period. Unfired clay, earth with sufficient clay content to be worked into shapes that harden adequately on drying, is one of the most universally available construction materials on Earth. Almost any soil with sufficient clay content can be used for construction without any processing beyond mixing to the right consistency. It can be formed into blocks, applied as plaster to wall surfaces, used to seal gaps in stone or wood structures, and used to create thermal mass elements. Dense wall sections that absorb and slowly release heat. In shelter construction, the oldest evidence of deliberately shaped clay used in non-ceramic contexts dates to the ancient period and includes small figurines and structured clay applications that document ancient familiarity with clay as a workable material. The discovery that wet clay could be shaped into structures that hardened on drying, that the ground itself could be transformed into a building material by the simple addition of water and the application of human hands, was a discovery with enormous construction implications that ancient humans appear to have made, at least in basic forms. The more sophisticated application of clay as a construction material, mixing it with fiber or straw to create a composite that resists the cracking that pure clay undergoes as it dries, applying it to woven frameworks to create cob or wattle and daub walls, combining it with stone or wood in hybrid construction forms, was almost certainly part of the ancient construction repertoire in regions where appropriate clay soils were available. Let's talk about fasteners and joining technology, Because no construction material becomes a structure without the ability to connect pieces together, and ancient joinery and binding technology deserves specific recognition. In modern construction, the primary fastener is the metal nail or screw, a standardized manufactured element that holds wooden or other members together through the mechanical engagement of a penetrating spike or thread. Ancient builders had no metal fasteners. What they had was a range of binding and lashing technologies that used natural cordage, plant fiber rope, rawhide strips, sinew, to connect structural elements in ways that were both strong and flexible. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Lashing is a more sophisticated structural technology than it might initially appear. The specific patterns in which cordage is wrapped around joints, the sequence of wraps, the tightening mechanics, the friction-generating arrangements that prevent loosening under dynamic load, are specialist knowledge that produces joints of very different strength and durability, depending on whether that knowledge is applied correctly. Traditional builders who work with lashing demonstrate the same kind of structural intuition about their joining technology that modern structural engineers demonstrate about bolted connections, an understanding of how loads are transferred, how failure occurs, and how to design joints that resist the specific loads the structure will experience. Ancient builders also developed direct wood joining techniques that did not rely on cordage. Mortise and tenon joints, where a projecting element on one piece fits into a corresponding cavity in another, are documented in ancient woodworking from the earliest periods where preserved wood allows identification. This joint type creates a mechanical interlock between structural elements that can resist forces in multiple directions, and its independent development in multiple ancient construction traditions suggests that it was a discovery available to any sufficiently observant and skillful woodworker. Here is something that connects all of these materials into a picture that is more than the sum of its parts. Ancient builders were not mono-material. They were not stone builders or wood builders or hide builders in the exclusive way that modern construction specializes by material. They were multi-material builders, selecting from the full range of available materials on the basis of the specific functional requirements of each element of each structure, combining materials in hybrid solutions that exploited the specific advantages of each. The mammoth bone foundation, with wooden post superstructure and hide covering, the stone windbreak base with woven grass roof, the wattle and daub wall, woven plant fiber panels infilled with clay. As a composite that achieved properties neither material alone could provide, the lashed wooden frame with stone floor and hide entrance cover. These hybrid constructions reflect a sophisticated materials understanding, a practical taxonomy of what different materials can and cannot do, and a creative engineering approach to combining them in ways that meet complex functional requirements. The ancient builder who looked at the materials available in their landscape and assembled from them a structure that kept 20 people warm through an Ice Age winter was not improvising desperately with whatever happened to be at hand. They were applying an accumulated, transmitted, field-tested body of materials knowledge and construction technique that represented tens of thousands of years of human building experience. They were engineers, working with a completely different material set than modern engineers, in completely different scales, producing completely different aesthetic results. But engineers in the fundamental sense, people who understood materials, loads, connections, and structural form well enough to reliably produce structures that did what structures are supposed to do: stand up, keep weather out, and make the inside warm. Let's come back to where we started. You are looking at the landscape around you. Autumn is coming. You need walls and a roof. You know what to look for, not because you figured it out today, but because you have been watching construction your entire life. Because the knowledge of what works has been transmitted to you through the accumulated experience of every generation that built in this landscape before you, because you carry in your practical memory a richer, more specific, more application-tested body of materials knowledge than any modern construction manual contains. You know which trees to take posts from and which to avoid. You know where the best clay soil is for infill. You know which grass species makes the best thatch, and when to cut it for maximum durability. You know how many hides you need, and in what configuration to cover the roof without gaps. You know how to lash the joints so they stay tight when the wind pushes against them. You start building, and what goes up is not magnificent by modern architectural standards. It is not beautiful in the way that designed buildings are beautiful, but it is exactly what it needs to be. A structure that works, built from materials that ancient humans spent hundreds of thousands of years learning to understand and exploit, assembled with knowledge that is as sophisticated in its domain as any modern engineering knowledge is in its own. Ancient humans built things, remarkable things, with remarkable knowledge, from remarkable materials. The sophistication is in the knowledge, not in the materials, and the knowledge was extraordinary.